Hello! In this video, we are going to prove the following theorem. For all integers n and k, where n is greater than or equal to k is strictly greater than 0, n plus 1 choose k is equal to n choose k plus n choose k minus 1. Now, before we get into the proof, what does this notation mean? Well, given any two integers a and b, where a is greater than or equal to b is greater than or equal to 0, we define a choose b to be a factorial over b factorial times a minus b factorial. So that's really what this means. Okay, so now let's get into the proof. To start off the proof, let's give ourselves two integers n and k, where n is greater than or equal to k is strictly greater than 0. And our goal is to show that this is true. And we're going to show that this is true through a chain of equalities. So let's start out by writing the right-hand side, because we have more to work with. Now, applying our definition, we have that n choose k is equal to n factorial over k factorial times n minus k factorial. And then applying our definition to this term, we have that n choose k minus 1 is equal to n factorial over k minus 1 factorial times n minus k minus 1 factorial. So just like that. Now notice n minus k minus 1 immediately simplifies to n minus k plus 1. And now what we're going to do is we're going to combine these into a single fraction. And to do so, we're going to get common denominators. So to get common denominators, what we're going to do is we're going to take the first fraction and multiply both the numerator and denominator by n minus k plus 1. As for our second fraction, we're going to multiply both the numerator and denominator by k. And now that we've done that, notice that n minus k factorial times n minus k plus 1 is equal to n minus k plus 1 factorial. As for this fraction, we know that k times k minus 1 factorial is equal to k factorial. So we have common denominators. So we can combine these two fractions into a single fraction. So just like that, the numerators were just added together. Now what we're going to do is we're going to factor out the n factorial in the numerator. And if we do that, well, in this parentheses, we're going to get n minus k plus 1 plus k. We see that the k's cancel out, so we're left with n plus 1. But then, n factorial times n plus 1 is equal to n plus 1 factorial. But then, this is precisely equal to n plus 1 choose k. Because if we apply our definition to n plus 1 choose k, well, what we get is n plus 1 choose k is equal to n plus 1 factorial over k factorial times n plus 1 minus k factorial. Just applying our definition. But really, this is equal to this. So this is equal to n plus 1 choose k. So through a chain of equalities, we have shown that this is equal to this. Right? We've shown that these two are equal. And since n and k were arbitrary integers that satisfy this condition, this means for every integers n and k which satisfy this condition, this is true. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.